Okay, it says it's being recorded. Okay, good evening. Welcome to the East Valley Astronomy Club meeting. We got a full house in the room, if you see through the camera. And I think we have a number of folks on Zoom as well. Hope you had fun with the swap meet. There were a lot of people, and I really appreciate all the folks who brought things to sell. And I appreciate all the people who are taking things home. I'm sure they do as well. So we are glad for that. And so welcome to our General Assembly meeting, February 17th. Normal agenda, we welcomes general business announcements. Our speaker tonight is Dr. Rolf Jansen from ASU. Do we have any visitors tonight? Yeah, stand up. Tell us what planet you're from. Tell James to go get this second microphone. Oh, okay. So Bob's the reason you're here. Okay, perfect. Other visitors? Okay, Amy, thank you. And Wisconsin is a lovely place to be from this time of year, so we're glad you're visiting. Okay, do we have others? Okay, so thank you. We're glad you're here. We always appreciate visitors. We have officers and board, and if they'll wave or stand up, I'm Claude Haynes, the president. Woody Sims, vice president. James Yoder is our secretary. Treasurer is Brooke Schofield, wetting his whistle in the back. And our board, Don Wrigley, Tom Mosden, Steve Bradshaw, Alex Beck, Dave Kosho, everybody's here. All right. And James Yoder is also the property director, and Marty Pazanka is our webmaster and newsletter editor. Events coordinator, we need you. We are looking for an events coordinator. I'm not going to lie and say it's an easy job, but it really is an important job. And we've got maybe 8 or so. I'll talk about events a little later in the slides, but we are looking for an events coordinator. If you are at all interested, please let me know. We can certainly train you and explain how to do it. It's not terribly difficult, but it does involve a lot of emails from people who may or may not understand astronomy. So that's the biggest issue sometimes is, oh, you mean it really does need to be dark? Not, we asked them to turn off the lights and, oh, by the way, they forgot to turn off the sprinklers, which has happened too. It's amazing how you can turn a 10-inch daub into a rain gauge in about 3 seconds. So let me know if you're interested. We do need somebody to help with events. It's really important, but we'll talk about it in a minute. It's also time to renew your membership. See Brooks in the back. We are always grateful for members who renew. There are a lot of expenses for the club, but we are always appreciative of the support that you do give us, either volunteering or through monetary support by memberships. Greco is not open tonight because it is not weather permitting. It is pretty cloudy, and I'm getting tired of this. I see Tom, he has done cloud measurements in the past. Is it just abnormally cloudy right now for us, or is it just my imagination? Okay, it's not my imagination. Thank you. We are looking for volunteers to help us. It's a lot of fun. Sometimes if you're saying, well, I don't know that much about the sky, or I don't know about operating the telescope, we can train you. One of the most effective people in the night when we are open is the person at the door. The person who greets people, asks them if they have been here before, invites them to come back, and just kind of controls the line. It's an essential piece of it, and you really don't have to know astronomy. You just can help us with crowd control. So if you have any interest at all, let me know, because it is fun. It's a great public outreach, and you meet really interesting people. Ask Don about the I already knew that guy who comes almost every weekend. But For this month, February 25th is the Gilbert Outdoor Expo, weather permitting, since last year it had a problem. Hopefully it's going to be fine. It's February 25th, 9 till 2. We will be doing solar viewing. They have lots of things: goat yoga, axe throwing. The Audubon Society brings birds, so if you want to be pecked at by a raptor, you can do that. It's really a fun event. There are just lots of interesting things there at the Outdoor Expo. If you need to buy a boat to go for your, if you want to go out to the middle of the lake and do astronomy, I'm not sure how well that works, but there are lots of fun things that you can do there. February 25th. Astronomy is the gateway drug to science. And we have started back with events, and they've been really busy. Steve Bradshaw is here. I saw Logan. I'm not sure. Brooks, Don, several. I'm going to skip some folks, and I hate doing that. But it is really fun. You get to meet a lot of fun families, not just the kids. We have a small petting zoo of meteorites that we now bring, and that has been popular. And again, you're only looking at one or two objects. So if you right now, if you can find the Orion Nebula, you're good. If you can find Jupiter, you're good. It'll, you'll be able to just find one thing. So again, outreach is really important to the club. Upcoming events, we have the Chandler Gilbert Community College on Thursday, hoping that it will be clear. Friday night, we have Faith Mather Elementary. We try not to do Fridays, but this was a large school that we've been to before. The 28th, American Leadership Academy. In March, the Apache Junction Superstition Sleepover. It's going to be held at their park, and at 7:30, we're going to be doing observing. On the 3/7, we ended up being double booked because we had a cancellation and it moved. Playa del Rey and Pomeroy. Some of you remember Pomeroy is a really great reading under the stars, and I didn't want to cut them out. So we could really use some help that night. And we've got some community associations, Ironwood Crossing and Viewpoint Community Association. Those are the closest upcomings. So if you can help us out with that, please send me an email, since I'm covering for an events coordinator. We could always use the support. It is always fun, and it's a really great signature piece of EVAC's outreach to the community. We really are noted for that, and it's really, really special and really fun to share your telescope with all sorts of people. I had a private star party last night with a 5-year-old and her great grandmother, somewhere between 95 and incapacitated, but she was able to walk and just kind of shuffle her way to the telescope, and she had as much fun as a 5-year-old. So that's the kind of thing that happens, and we really do encourage you to help us with that. James is going to chat for a minute about a future rental program and get some input from you.
Yeah, so we're considering maybe starting up a rental program. Considering starting up a rental program with some equipment that maybe is, we realize most of you guys already have telescopes and stuff. So maybe some stuff that would be a one-time use, like collimation tools or something like that. Or maybe if you're considering planetary imaging, we're thinking about putting together a package that would have the camera, the computer, everything you'd need except for the telescope, and the software to do it, so you could test out. The rental program would be probably for about a week. You'd rent the equipment for a week at a very reasonable price. We also are thinking about getting a telescope or two that could be used by, we're also teaching astronomy class by students there, or possibly rented if the students aren't using it for renting for the class. So anyway, the point of this slide was to try to gauge kind of interest in what, if members thought this was a good idea, that we should proceed. And if you had other recommendations. Another thing I just thought about recently is for imaging or even viewing, there's a lot of different filters out there and stuff. You don't know which one to get. We have a lot of experts on astrophotography and stuff. Maybe we could get one or two filters that you could rent out for a week and test it out and see if it works for, astrophotography or even just viewing, that kind of stuff. So wanted to kind of get a gauge, a raise of hands, maybe of how many people think that's a good idea. You know, we don't want to do this if it will take some effort. If it's something that won't get utilized or you guys don't think it's a good idea, we don't want to waste the money on it. So a raise of hands who think that that might be a good idea, perhaps. Okay. Yeah, we realize that probably most of you guys have telescopes already, but you know, if you're thinking about a go-to telescope and you don't have one, the one we're thinking about getting would be a basic go-to telescope. So how many of you think would you might be interested in maybe the telescope aspect of it? So a couple of people, and that's fine. Don't feel bad. Don't feel like you have to raise your hand. Planetary imaging a package, again, like I said, all you need is the telescope and everything else that you need to go with it would be provided. 1, 2, 3, 4. Okay. So, and then other accessories like collimation, maybe filters, basic filters to see if you'd be interested. Anyone would be interested in that? And if, okay, so I think there'd probably be need. The other thing is we're open to ideas. So if you have anything, do you want to give them a couple of seconds to maybe voice some opinions or just email? And you guys have any ideas of other things that we might want to consider? Send me an email or send, you know, the club an email. Yeah, send me an email. We're absolutely open to doing other things. So.
A couple online thumbs up too.
Okay, good deal. Any questions? Okay, thanks.
Yeah, this came out of James doing the beginning telescope class. We've done a couple of those. And also from a survey we did last year, we just weren't able to kind of do all of the things that were in the survey. So should be a fun idea. List of badges awaiting owners. Brooks has boxes of badges. Even if it's not yours, just pick one up. He'll be glad to get rid of it. You know, it's handy. You know, I don't use my name at a restaurant because nobody can spell Claude and Bob is easier. It's Bob, don't worry. So if you want an alias, you are set to go. Please don't steal their identity. Okay. Mike Tovar from ASU. Mike, come on up.
Hello, everybody. First off, I would just like to thank Tom for sharing my request on Facebook about being an Eclipse ambassador, and also to Claude for giving me a few moments of your guys' time today in the meeting. So I am an undergraduate at ASU. I'm earning a astrophysics degree, and I have been selected by the Astronomical Society of the Pacific to be an Eclipse ambassador. Now, what I'm tasked to do now is find a partner who is a amateur astronomer, which is why I reached out to this club. I've been to a few meetings before, enjoyed them, and was a paying member for a short time, like in the mid-10s or so. So I figured this would be a great place to reach out. As an Eclipse ambassador, there's about 15 to 20 hours of work that would be done between now and 2024 by the last solar eclipse. That ranges from meetings with me and virtual meetings with the Astronomical Society of Pacific. And those are aimed to give guidance as to how to reach out to the community to prepare the community for the upcoming eclipses. One of a few benefits that come along with this is we don't have to pay for materials. All of that would be sent to us. But then also you earn official recognition from NASA as an Eclipse ambassador. With that, you get a badge, a nice little certificate, and then a letter to the club stating the work that you did for these eclipses. And also you get a 1-year membership to the Astronomical Society of the Pacific. So I've never done any public outreach like this before. So anyone who has experience in this area, I would definitely appreciate any help that you could offer. And I think it'd just be a great opportunity to share with the community how they can view and the science behind the eclipses that are coming up in the next few years. That's it. Well, also the email that Tom provided in the Facebook post is a good way to reach me. It is the number 82 Tovar, Tov as in Victor, AR @gmail.com. You can reach me through that. By the end of the month, I need to find a partner. But it's no stress on you guys. If I don't find anyone, ASP will hook me up with someone that's in the community. So it might be one of you anyways, so might as well volunteer. But joking aside, like I said, I enjoyed coming to these meetings, and people here were great. So I figured I would just reach out to you guys to help me out. Thank you.
Mike, if you have two people that wanted to do it with you, is two okay, or are you just limited to one?
I mean, I would take the extra help. I think officially it's just one amateur astronomer, like for the certificate and badge and all that kind of stuff. But yeah, I mean, the more the merrier. Absolutely. Thank you.
Thanks, Mike. Good luck.
Okay. So I have a kind of a fun announcement. I'll do first. Michael Popri is over in the corner. Wave, Michael. Michael is the new president of the Saguaro Astronomy Club. And so if you are interested in Saguaro astronomy or just want to chat with him, he'll be available for a bit, I bet. But because Saguaro has been having some troubles recovering from after the pandemonium, we have decided to sponsor the Messier Marathon this year. So it was one of those where we just didn't want to not have it. And it was going to be difficult for SAC to put it on. So EVAC has volunteered to sponsor just for this year, and SAC will have a chance in the future. And if you don't know, it's a wonderful contest to try to find 110 things we shouldn't be looking at. They're not comets, which has been really useful now with the Great Comet. When we show people that, then we would say, gee, what does that look like? Oh, it looks like M31, or it looks like some other objects, or M42. Because then you could say, oh yeah, this is your object lesson of why he made the list. It looked like a comet. We also have a new location. It was just approved this week. It is north on Hovatter Road. It's about 3.5 miles north of the exchange. So you see the airfield down here, which we can no longer use. Boo. And over here is the antenna site that SAC uses. This one is a dirt road, fair, it's level, no big washes or anything to go through. Nice big desert plain, less dust than the airfield because it's a little more rocky. But we'll give you some information on that because we only figured this out this week. And so check the newsletter, check the website, check other announcements for that. We'll give you the details, but do save the date for March 18th. And now, anything else? Anybody has any other thoughts? And if not, Woody, would you introduce our speaker? And I'm going to give you that, and I'm going to set up his stuff.
Hi, I'm Woody Sims, your club VP, and I'd like to introduce Dr. Rolf Jansen as our featured speaker this evening. He's a research scientist in the School of Earth and Space Sciences at Arizona State University. He received, it says he received, I think he earned his PhD in 2000 from the University of Groningen, close, in the Netherlands for a study of the variation of spectroscopic and structural properties of representative sample of nearby galaxies of all types and luminosities. Sounds like that pretty much covers all kinds of galaxies. After a brief postdoctoral stint at the European Space Agency Center for Science and Technology, he joined ASU in 2002, initially as an HST postdoctoral research scholar, and was subsequently appointed as a research scientist at ASU. His research interests include galaxies, near and far. Seems to be a theme here. and how they're assembled and evolved over time and what makes them tick in terms of the physical processes at play. He serves as a principal investigator of the HST programs and as a co-investigator and team lead on the James Webb Space Telescope program to develop the JWST NEP time domain field. I hope he tells us what that's about. And as a co-investigator of many studies at other wavelengths. Please welcome Dr. Rolf Jansen.
Thank you, Woody. And thank you all for the opportunity to tell you something about this. Oh, yeah, perfect. Okay, thanks for this opportunity to tell you something about this new space observatory that we got. And that after such a long wait is actually delivering the fantastic data that we were all hoping for. So I would like to break down this talk in three major parts. First, I'd like to introduce, or for many of you probably recap, some of what JWST, the James Webb Space Telescope, is, why it's there, where it is, and wow, it works. And then I'll move on to a particular field in the sky that I'm interested in and show you at the end lots of nice pictures. So the James Webb Space Telescope, JWST for short, is a large infrared observatory in space. And it consists of the payload, a large telescope that is sitting in the perpetual shade of a sun shield. And then on the warm side of that sun shield is the actual part that makes the observatory work as an observatory in space. It's the spacecraft bus with all the equipment needed for energy propulsion and communications. And first off, JWST is a very different space telescope than any other telescope that has flown before in space. It is, in many respects, the scientific successor of the Hubble. But the first thing you'll notice is it does not have a telescope tube. It's completely open and unprotected. And that makes it very different, not just how it looks, but also to some extent to how it operates. That open telescope structure I just mentioned. The other thing that's very different is that its primary mirror is not a single circular piece of glass or other reflective material. It's a segmented mirror that's built up out of 18 separate segments that each are hexagons as well. And they together form this very large reflective surface, this primary mirror. Each of these segments is made out of beryllium, the lightest possible machinable metal. And it has this special property that if you cool down this material to cryogenic temperatures, it stays extremely stiff and it keeps its shape very well. The front surface of each of these segments has been coated with a very, very thin layer of pure gold. The whole observatory has about 48 grams of gold evaporated on its surfaces. But the reason that it's gold and not aluminum or silver is that it needs to be reflective in infrared light. And gold is by far the best reflector in infrared light. The JWST primary mirror is far larger than Hubble's. It's about 2.7 times wider in diameter, 6.5 meters, so more than 21 feet. That gives it a light gathering power that's more than 6 times larger than Hubble's. That sun shield that I talked about is about the size of a tennis court. Okay, you have to cut off some of the edges, but still, for practical purposes, it's about that. And that allows the telescope to passively radiate away its heat energy to space and cool down to just below 40 kelvins without the need for any cryogens. And that temperature, about 39, between 32 and 39 Kelvin, that's colder than the surface of Pluto, at least many parts of the surface of Pluto. Of course, if you have such a large telescope, you have a problem. How do you get it up there? There is not a single rocket fairing in the world that's operational that can house a 6.5 meter telescope in one piece. So the largest and most reliable rocket that was available had a fairing of about 15 feet in diameter, 5 meters. And that meant that the whole telescope was designed to be folded up, launched in this origami state, and then once it's in space, to unfold in stages. And the fairing is that aerodynamic nose cone and the payload container that sits on top of a rocket. So JWST is sensitive to infrared light, as well as a little bit of the reddest portion of the visible spectrum. And it has 4 instruments that observe that infrared light and unravel it in various ways. And most of these instruments, they do double duty. They can both function as imagers and they can function as a spectrograph. And there's also quite a lot of redundancy between capabilities of these instruments. First off, there is the camera, the NIRCam, near-infrared camera. It is actually a double system. It has 2 completely independent copies of itself, 2 modules that each have 2 channels, a short wavelength channel and a long wavelength channel. And they each give an area of the sky that you can image, and they can be operated either in conjunction, in which case you have a larger field of view on the sky, even though there's some gaps in between the individual detectors, or you can operate them separately. Suppose that you want to take really, really fast observations of something and you have a high data rate, you can turn on only 1 module or even only 1 detector. The NIRCam instrument also serves as the wavefront sensor for the observatory, because once every while you have to check that all these separate mirrors are still in alignment, that they still form this one single reflective primary mirror. And it has, through that wavelength sensor part, has also spectroscopic capabilities. The next instrument is an actual spectrograph from the ground up. It can take spectra of not just one object. It can do it for up to 100 at a time. And it can do that in various ways. It has a programmable array of micro shutters. And you can build your own little spectrograph slit out of those shutters, or some aperture with pretty much any arbitrary shape out of those shutters. And there's 4 of such micro shutter arrays that together give you a usable area of about 3 by 3 arc minutes on the sky. But it also has little slits, and it even has an integral field unit. Now, if you have an object that is extended and you want to map how things change within that object, say line ratios, for instance, or where there is star formation going on in these objects, then you can put an integral field unit on that object and get a spectrum for each little pixel that's mapping onto that object. The next instrument is the mid-infrared instrument. And while the previous 2 instruments, they operate in the same wavelength range between the far red and the optical, about 0.6 microns to 5 microns in the near infrared. But this instrument goes way beyond that. It can operate all the way to 28 microns. And in order to do that, it has to be cooled considerably further down than all the other instruments. So that can no longer be done passively. So this instrument has a dedicated cryocooler to bring down the temperature to about 7 kelvins. And that means that at these longest wavelengths of about 28 microns, you're not blinded by the glow the heat of the telescope and the instrument itself. Just like all these other instruments, it has multiple modes of operation, and that includes coronagraphic imagers that can blot out the light of a very bright central point, say a star or an AGN, and then look what's around very close to that bright object. And it can get low resolution spectrometry, which is essentially low resolution spectroscopy over a slightly shorter wavelength range that extends to 12 microns. And last but not least is there the fine guidance sensor, FGS, and near infrared imager and slitless spectrograph, NIRIS. So this instrument does double duty. It houses a camera dedicated to sensing whether or not the telescope is still pointing exactly where it needs to point, using guide stars. But then the other part of the instrument is a full-fledged imager and a slitless spectrograph. Now, in slitless spectroscopy, you don't have any slits. You get a dispersed image of every object in the field. And effectively, every object gives a little spectrum in the output of that instrument. And that allows you to discover things where you don't know a priori where interesting objects are, or if you know that there is something in this field, but you don't know its exact position, you can use slitless spectroscopy and still do the science. So it has an added discovery space or discovery parameter space to it. It has the exact same filters in its imager as are housed on NIRCam. So that's part of that redundancy. Suppose that something goes wrong on orbit, then you don't lose the whole observed tree. You still have the capabilities there, just over a smaller field of view or with slightly less resolution. So why do we need this observed tree? It's horribly expensive, everybody knows that. But to start to answer that, I have to go back a little bit into my childhood. I was, from very early age, I was interested in pretty much anything space and astronomy related. But while I had seen with my naked eye some planets in the sky, I had never seen myself the Milky Way. Where I grew up, the light pollution was horrendous. So I had to just imagine that it was out there. I read books, and the typical pictures that were shown of astronomical objects like galaxies, they were pretty stark, just black and white images from photographic plates that don't show really what's there. You have to imagine what these objects are like. And then Hubble happened. And it turned these stark images into wonderfully colorful objects, whole worlds. And it gave us a much darker sky, so you could see fainter things. It had a higher resolution because this pesky atmosphere is not in between you and your telescope that blurs everything. And it allowed access to wavelengths that are blocked by our own atmosphere. So a galaxy like M104, the Sombrero Galaxy, turned from that black and white blob into something with lots of colors, glowing gas and intricate filaments of dust that absorbs light. Hubble also discovered that every major galaxy has a supermassive black hole at its core. And it's not just the really, really big galaxies, but even galaxies like our own, or the Andromeda Galaxy, our closest neighbor. We didn't know anything about that before Hubble. Hubble gave us sharp views of dusty star-forming galaxies, star-bursting galaxies, where we see how intricate this interplay is between gas that always has dust associated with it, star-forming regions that destroy that dust, blow out that dust and gas, and make their surroundings glow. And then at larger distances, you might find these filaments, these tendrils of dust that have been blown away from these star-forming regions. It showed us also interacting galaxies, merging galaxies, where in many cases, the areas where most of the activity takes place are not the brightest ones in this image. The areas with most activity are actually hidden behind all this dust. I wonder what's going on behind that. You need longer wavelengths for that. And it showed us over a tremendous span of time, pretty much about 12 billion years. It showed us how galaxies assembled and evolved over time. So in this one image, you can pretty much trace 12 billion years of cosmic evolution. But if you want to know, okay, from where are the first galaxies that were forming, then it turns out that to find galaxies at redshifts larger than 6, 7, 8, you have to look really hard. It's incredibly hard to find those because those galaxies will be dim, they will be extremely red and tiny. And they're so rare that you can find maybe a handful in an entire swath of sky like this. Because the universe is expanding, light that gets emitted from distant objects gets stretched on its way towards us. So ultraviolet light from these objects gets stretched so much that by the time it arrives at Earth, at our telescopes, it's no longer ultraviolet light, it's near infrared light. And as soon as you get to redshifts of 7, 8, the wavelengths of light have become so long that Hubble is no longer sensitive to those. Also, because they're so far away, they're dim. So Hubble is just not a large enough mirror anymore to collect enough photons. And then hand in hand with the size of a primary mirror goes also the maximum resolution you can attain. Bigger mirrors can see sharper, at least in theory. And if you want to see what's going on into a tiny little speck of light, you need higher resolution. So all these things is why you need a new space telescope. The James Webb Space Telescope was designed just for that, to look and open up this near-infrared regime beyond where Hubble can see. And it has been a long wait. I got involved in JWST about 2002. And at that time, we thought Hubble would be launched by 2007, maybe even 2009. And that, of course, turned out to be not quite the case, a bit optimistic. But then finally on Christmas Day, 2021, it lifted off. On top of an Ariane 5 rocket, it was launched from Kourou in French Guiana into orbit. And this was one of the goodbye pictures from the actual launcher, the rocket. Sees what at that point is still the spacecraft all folded up. So you see just the back end of the spacecraft bus. And the first thing that we knew from, okay, we might have a telescope was when it unfolded its solar panels really early. So we knew, okay, it knows where it is, it's gave the okay, and it starts unfolding. The Ariane rocket for this particular launch launched the telescope so precisely that almost no fuel was needed to get it into the right orbit. And that orbit is a wide halo orbit, sort of a Lissajous orbit around a special point in space called L2, the second Earth-Sun Lagrange point. And in that position in sky, which is an unstable point, but if you're there, the added gravity of the Earth together with the gravity of the Sun makes you go around the Sun in exactly 1 year, just like the Earth. So there's a special place where you can park a telescope and always be in a direct sideline to the Earth. And more importantly for JWST, you can put a sun shield in a fixed place, always between your telescope and the Sun and the Earth and the Moon, such that that telescope never sees the glare of those bright objects. Because so little fuel was used to actually get to the right orbit, all that excess fuel, that reserve fuel remains, and it can now be used for station keeping. So that makes the potential extent of the mission quite a bit longer than we could have hoped for. So that's great. Now, the downside of this area is it's so far away, it's about 1 million miles away from Earth, is you cannot get astronauts there. So the idea of having a manned surfacing mission to this telescope, that's a pipe dream. That's not going to happen. So from the get-go, this telescope was built with redundancy in mind. So once all these scary 400 single point failures were checked off on its way to this point and during commissioning, we know that if something fails, we have redundancy. That mission will not end because of a failure. And then, of course, about 7 months after launch, so we had a month to get to L2, we had about 3 months to cool down, and about 3 more to get all the mirrors aligned precisely, to commission the telescope, to commission the instruments. The first image, the first science image of this telescope was made public. President Biden scooped NASA and kept the honor of presenting that first image to the world himself. But it's amazing what you can see in this image of a massive cluster. It's a southern galaxy cluster. That's why it's called SMAX 0723, and then some extra digits to give its position in the sky. And this cluster is so massive that its combined gravity acts as a lens for objects in the background of this cluster. So many of these strange reddish objects in the background have been distorted and magnified by the gravity of this cluster. And there's a lot of red objects, intensely red objects, orange objects, most of which are invisible or incredibly faint to Hubble. What this image also showed was that the James Webb Space Telescope not only meets its requirements, it far exceeds them. During the whole design and testing of the telescope, we were not allowed to test for performance shortward of 2 microns. It needed to perform at a wavelength of 2 microns and beyond. And anything shortward of 2 microns was supposed to be just like an added bonus. Well, it turned out that they ground all these mirror segments and all the optics so well, and they aligned them so well, that even at these shorter wavelengths, it performs almost as if it's a diffraction limited telescope. That means that the shorter near-infrared wavelengths, it outperforms Hubble in sharpness, at Hubble at optical wavelengths and ultraviolet wavelengths in sharpness. So, having introduced or recapped what this telescope can do, at some point 4 or 5 years ago, we started wondering, can we do time domain science with this telescope? Can we do survey time domain science, like looking for things that vary in brightness or that move, even though the telescope was not particularly designed for it? And is there a good reason to even want to do that? So, first of all, what is time domain science? Well, while from our perspective, it often looks like the sky is unchanging, if you correct for the diurnal and annular motion of the Earth, then we often think of the sky as fairly static. But there's lots of astrophysical phenomena that can cause an object to either change in brightness or to move. That can range from variable stars, which may get brighter and fainter in sometimes a very regular pattern. It can also be like novae and supernovae and gamma ray bursts, which are transient. So they appear and then they fade away and disappear at various rates. Active galactic nuclei, they vary. They tend to flicker. The active galactic nucleus is a tracer of the supermassive black hole in the center of galaxies. As matter falls into that supermassive black hole, its accretion disk flares up and dies down. It's not a very steady progress. It's like supermassive black holes are messy eaters, and you can see that by tracing the brightness of AGN. much nearer to home, the orbital motions of asteroids and comets can be traced as well. It makes objects move through the sky. And if your telescope is big enough, if you're sensitive enough, you can do this really, really far out to the Kuiper belt if need be. So one of the interesting things that we didn't know about when the telescope was designed was that we sometimes get these interstellar visitors, like Oumuamua. I don't know how to pronounce that correctly, or what first was thought of as a comet, Borisov. They are visitors from interstellar space. Through just their proper motion, you would be able to tell them if they're coming in on an almost radial orbit. You can also look for nearby stars and brown dwarfs. They will tend to move slightly with respect to the background stars in our own galaxy. So there's, if you think of all these different kinds of objects and all these different kinds of phenomena and just bunch them all together, you're talking about time domain science, or something you can call time domain science. So in the past years and in the near future, various facilities came online on the ground and in the near future in space that were designed to do time domain surveys. Examples are the Pan-STARRS survey or the Zwicky transient factory that looks for transients over a large swath of sky. But in the near future, next couple of years, we'll probably see the launch of the Nancy Grace Roman Space Telescope. And on the ground, the Vera Rubin Observatory will be commissioned for its LSST survey. And all these things, again, they cover solar system, our galactic neighborhoods, but also objects at cosmological distances and very large look-back times. So what can JWST do there, and would it add anything that's useful? So with the back of the envelope calculation, you can sort of figure out, okay, well, what would these other observatories that are purpose-built for time domain science, what would they deliver? And it turns out that for most cases, you're limited to objects that maybe are 23rd, 24th magnitude at most, because what's relevant here is not how you add all the images that you can take together, but what you can detect in a single epoch. And it turns out that in 15 minutes to an hour cadence, you can search with these facilities large fractions of the sky and do that maybe either several times per night or once every few days. So we need to do something that's way different than that. Otherwise, we don't add anything. As it turns out, JWST NIRCam could do similar things in similar timescales that are about 3 magnitudes or more fainter than that. So that's a new survey discovery space or parameter space. There's a caveat though. You need to have a suitable survey field because it cannot do it everywhere in the sky. So it's an unexplored magnitude range for variability studies and an unexplored regime for proper motion detections. Possibly we can detect something that moves as little as 0.5 milliarc second per year. That's tiny, tiny movements. But if your observatory lives for 10 years then or more, then that becomes not that hard to do. And it would be exciting to detect, say, incoming interstellar asteroids when they're still beyond the orbit of Neptune, in time that you might actually mount a campaign to observe them or maybe even go there. So where can JWST do time domain science? Now, it turns out that for most areas in the sky, the combination of avoiding the sun and keeping the telescope in the shade and still have power by shining sunlight on your solar panels, that you have only 2 separate periods per year that you can observe an object in an arbitrary area of the sky. Also, as of the current or the upcoming cycle of observations. We are strongly discouraged to point the telescope in the meteor wind, just to mitigate the number of meteor impacts on the mirror. But there's two special regions in the sky, very near the north ecliptic pole and the south ecliptic pole, which corresponds to the orbital poles of the observatory. There you can go any time of the year. Because observation with this telescope is different than observation with Hubble. Here, the date of observation dictates at what orientation you will observe this particular object in the sky. Observers cannot just say, well, I would like to have this orientation. For some objects it may work, for other objects it may not work. So that limits how efficient you can observe, or when you can observe, or how efficiently you can use observations with instruments in parallel. Except for these special areas in the sky, where you can go always. And throughout the course of a year, you will get any position angle, any orientation you might want. And that's good if you want to put a spectrograph slit on an object that has a neighbor that you definitely do not want in the slit. You may need specific orientation there. So if you want to have a JWST time domain science field, then that implies that you need to be in one of these continuous viewing zones near the north or the south ecliptic pole. And that means that existing fields from Hubble, from Chandra, from big ground-based surveys, they will not do. We need a new field. So let's take a look at these two special areas in the sky at near-infrared wavelengths and see what kind of interference from galactic dust and clouds are there, and whether we need to worry about bright stars there. So I compare here at the top the area around the north ecliptic pole, and at the bottom the area around the south ecliptic pole. The first thing you'll see is that there's this big bright thing in the bottom left panel. That's the Large Magellanic Cloud. It turns out that it juts significantly into that area, and it blocks our view of the distant universe. So great for LMC science, not so great if you want to do a cosmological survey. The other thing is that if you look at the middle panels and compare the top and the bottom, there's a lot of blue and purple in the top. That corresponds to clean areas where there's not a lot of dust and gas in between us, and where we have a relatively clean sightline out of our own galaxy. Whereas at the bottom, again, that big white patch and everything around it, that's the Large Magellanic Cloud. And then there's also quite a lot of galactic structures that sort of go in that direction. And then the right panels, although that color scale is not particularly informative, but it's for a reason. If you have a good area with not too many bright stars that might blind JWST, then the color should be blue. And the first thing that strikes you here is that there's almost no areas that are blue. Pretty much everything is unsuitable. But there's a few patches in the northern area that are blue, that are really clean, that there's no bright stars that would blind JWST, and where you could, and that are large enough in size that you could put a nice survey field there. So there's no solutions for a time domain field in the southern sky, except if you want Large Magellanic Cloud time domain science. And the very best region in the northern continuous viewing zone has, as it turns out, good guide star solutions also for Hubble. This field happens to be at the edge of the continuous viewing zone also for Hubble. So that's great. You can have uninterrupted observations there with Hubble. And there is a bright quasar in this field that can serve as a phase calibrator for radio interferometric observations. So we have sort of other wavelength ranges covered that way. And it has a low galactic foreground, so little extinction there, a clean sightline out of the galaxy. And just for completeness, I give you the coordinates here. a slightly different way of viewing at this is, okay, well, where in the sky is this? So this bright band here is our own Milky Way. It's the midplane of our Milky Way and the gas clouds that jut to either side from that midplane. So we're actually quite low above. We peak out above that midplane, but we're not pointing at the center of the galaxy. We're pointing sort of away from that. But we're about 30 degrees out of the plane, the midplane of our galaxy, where we're within that special region where JWST can observe all the time. This means that this area will also be good for galactic science, because if we're looking at a shallow angle out of our galaxy, then the sightline through our galaxy, even though it's clean, will have still quite a lot of galactic stars in our bulge, in our halo, in the thick disk. So we can also do galactic time domain science here. But we first had to prove, of course, that this was really a good field, that there's nothing strange going on, that the absence of bright stars is not because there's a big fat dust cloud sitting there. So we went to the Large Binocular Telescope in eastern Arizona, and we looked in the optical all the way through about 1 micron to make sure that this was indeed a good extragalactic field. And yay, it is. No bright red stars or near-infrared bright stars, so excellent for deep extragalactic science. And we got some preliminary near-infrared data from the ground as well, even though that's not quite as deep. And we verified with the VLA in 2 different configurations at a frequency of 3 gigahertz or about 10 centimeter wavelength, that this was also a good radio field with nothing strange going on there. So once we know from this is great, that's nice, but you need to convince the community that it's great, that everybody's on board and that this is the best field and not just a field. And it turned out that that was surprisingly easy. As soon as we had identified this, some colleagues, particularly in the X-ray community, they jumped on this field and were very successful in getting Chandra and NuStar and recently also XMM observations in this field. So NuStar is a hard X-ray space telescope. Chandra is softer X-rays. And for both of them, these are now viable deep fields in X-ray. For NuStar, it's even the deepest field in hard X-rays in the sky. But we got proposals awarded across the electromagnetic spectrum, from X-rays all the way to very, very long wavelength radio. LOFAR is a very large multi-country interferometer in Europe that observes very long wavelength radio emission, and pretty much anything in between. We also got some ground-based spectroscopy just to anchor to see whether there's any kinds of large-scale structure in this field that we can already identify. So my task in all this, after selecting the field, was to start the campaign with Hubble. So even JWST is great, but let's not forget about Hubble, because the 2 facilities are complementary to each other. So in 2017, 18, 19, we had a pilot study of the central portion of this field, where we took 2 cameras on Hubble, the ACS wide field camera and the wide field camera 3 UVIS. And what we did was we densed these 2 cameras around the field center such that we could operate them both and get eventually useful overlap of the coverage of these cameras. And ACS cannot observe ultraviolet radiation, but it's really, really sensitive for visible radiation. Wide field camera 3, on the other hand, can do ultraviolet. So what we did was we took 1 ultraviolet filter that cannot be observed from the ground because it's shortward of the atmospheric cutoff, and then 2 filters in the visible, both still shorter wavelengths than where JWST would operate, and then dense these cameras around until we finish this inner circle. And in order to plug this central hole, we have 1 extra field that sort of juts out to make that work. the color rendition in this image is such that I gave what is actually sort of yellowish, green yellow light. I gave it a red color. And what is really a blue light, I gave that a green color, such that ultraviolet light could be put in the blue channel and that we could create a color image out of it. This, of course, happens a lot. Cameras can observe wavelengths our eyes cannot, but in order to represent it, we try to compress it somehow into something that falls in the visible rainbow of colors. And there was a bunch of undergraduate theses at ASU that resulted from that data in one way or another. And then in subsequent cycles, we said, okay, now since this works, let's do a similar strategy for the outer area, such that we can cover with Hubble any area where JWST is likely to observe. So we created this annulus around this inner area. Again, we danced these two cameras around, and it turned out that over a cycle period, about a 2-year period, you can dance these cameras such that you can fill in that whole annulus. Now, the annulus has a little bit of wonkiness to it, because even though at most positions you can get a nice guide star for Hubble, there's other positions where that doesn't quite work out. Also, since we wanted to use this continuous viewing zone of Hubble as well as JWST, and since we're near the edge of where that continuous viewing zone of Hubble is, we were limited in our choice of where and when to observe that. So that creates a little bit of irregularity. It's not quite round. And there's currently a PhD student working on trying to see what's going on in this field in terms of variability, just with the Hubble data. The colored areas there are the last observations that took place, and they happened at the end of October this past year. So that completes the coverage with Hubble. For reference, I show here the same fields, but with areas overlaid that represent the areas that will be observed with the James Webb Space Telescope as part of a guaranteed time program by Professor Roger Winters, who is one of the interdisciplinary scientists for JWST at ASU. And there's 2 of these rectangular areas that are given here in solid, slightly lighter orange. Those have now been observed. And the 2 that are still dashed, they will be observed. This top one will be observed Monday night. And this one will be observed sometime in probably early June. Now, this field is large enough that it's very hard to display this on a screen and still see anything. There's just like 22,000 pixels across. There's no way of representing that. So what I show you from the Hubble data alone here is some cutouts of interesting objects. So this is by far the brightest and largest galaxy pair that's in this field. And clearly they have very different colors. One of these galaxies seems to be much bluer or bluish greener than the other, which seems to be much redder. And there's some galaxies even in the background. This galaxy here is behind this big spiral, this one also. And they have a very intense red color with just the Hubble filters. But there's a lot to see there. There's sometimes interesting superpositions as well, where one galaxy is sort of blotted out by another galaxy that's in front of it. And there's a very large color difference or range in color in this image. There's clearly objects that are very, very red in Hubble filters, whereas others are intensely blue and bright. So that means that they're bright in UV light. And of course, you have a menagerie of shapes. You have galaxies of all kinds, depending on what the intrinsic nature of these galaxies is, or how far away they are, and what kind of stage of assembly or evolution they are. There's also quite a lot of objects that just look like little points. Those can be either stars in their own galaxy, or they can be quasars, where they're so far away and the core is so bright that we see them as point sources. We just are not sensitive to pick up the fuzz of the galaxy itself that's around it. And one of the reasons why we really wanted that UV filter was to figure out, okay, from what are the sites of the most intense star formation, where the star formation has already blown out most of the dust, such that you have a good sightline to those regions of newly formed stars. So for instance, in this galaxy, there's intensely bright patches that are larger star forming regions than anything that you would see in the local group. So then comes JWST. And the first area that we observed as part of this guaranteed time program was what we call a spoke, a rectangular region that consists of two separate pointings that are partially overlapping each other, and that point more or less downwards in this composite of the Hubble image, one of the filters of the Hubble image. What we had wanted was a nice rectangular area. But when the second part, that second area of the 2x1 mosaic, when that was observed, it turned out that the guide star that was selected was a double star, and the guide got confused. And once JWST gets confused, it takes the safe route. It stops your observation and moves to another observation. You're done. So that was not good. So we said, okay, hey, wait a minute. That was not our fault. We did not select that guide star. The system did. Can we do it again? And luckily the answer was from, sure. But the soonest that we could get on the flight calendar again was about 2 weeks later. Now remember that I told you before that the date of observation dictates the orientation that you get on the sky. That's why there is this weird kink here between the first part and the second part of this mosaic. But we still got more or less what we wanted, just not quite. It gives a nice artistic view of this field. Let's put it that way. So if I take that vertical spoke and if I rotate it now, then you get something that we used for a press release in December. And this is the first image where we combine 11 filters, 3 filters from Hubble and 8 filters from the NIRCam camera on the James Webb Space Telescope. And that covers everything from ultraviolet light all the way to 5 microns in the near infrared. So there's no way that our eye can see that. Almost all of the wavelengths shown here are outside of the range that we see. So I had to crunch that whole wavelength range into where the visible spectrum is, assign a different color to each filter, such that I get a nice rainbow up here, or each filter has its own unique color, then combine all these images together and see what we got. So in a sense, this is a hypercolor rendition of this field. And the first thing that struck us was that all these galaxies, they seem to have fuzz around it. They have halos, they have streams of stars. You can almost visualize how these galaxies came to be. That was something that reminded me a lot of numerical simulations. Like if you go to simulations of the universe to see how matter comes together and how galaxies are formed that way, you get that sort of streams. And I can zoom in on that and look at some particularly interesting objects, which is sort of aligned all the way around, and look at a little bit more detail of what's going on there. So what we see in some cases is just serendipitous, spurious. This middle galaxy has actually nothing to do with these 2 galaxies. It's at a different redshift. It just happens to fall along the same line of sight. But all the fuzz that's between these 2, that is in fact associated with these 2 galaxies. They are in interaction with one another. These things will come together eventually and form a very big elliptical probably. In other cases, it's not even clear what's going on. There's so much going on there. Lots of superpositions along the line of sight, lots of interactions where we see morphological evidence that these galaxies really are interacting with one another. And then in the background, we see so much stuff, all kinds of different objects that may be train wrecks, like objects that are much smaller than a full-scale galaxy, but are still coming together. And there's lots of these things. We cover everything from very intensely blue objects that are probably quite nearby or intrinsically extremely UV bright, to things that are so red that Hubble did not even detect them. Like anything that looks dark orange or red in these images, Hubble cannot see. It's beyond its wavelength range. And a lot of the other things, Hubble cannot see because it's too faint, or the surface brightness is too low. So it helps to have that really, really big mirror to collect all those photons and show us what's there. It's reminiscent to when you go to a large city and you see the city doom up from the distance, all you see is just the skyscrapers. That's what I think of as Hubble. It sees where stuff is, but it doesn't see everything that's there. Only when you approach that city, you'll see that there's all these suburbs, all these other buildings there that form the whole city. We know that there's something there because of that skyscraper, but with JWST, we can now see the city. And these images, when this image first was put together, all these colors, I just spent days just looking at it, trawling from object to object through this image. It's just so spectacular. And because the telescope is functioning so well and it gets such sharp images, it means that we can see a lot of detail in these galaxies, even though they're very far away and in many cases very small. Also, the same sharpness helps that all the photons you do collect get concentrated into a nice sharp point spread function. So you can see very faint point sources too. You may know that most stars that are observed by JWST, they are characterized by these diffraction spikes. And because of the way that the primary mirror consists of these hexagonal segments, and because the support structure of the secondary mirror forms this threefold symmetry, you get 6 diffraction spikes in your images. But because we got this little twist in our orientation, wherever there's overlap of the 2 separate points, we get actually a double set of diffraction spikes. So here you see something that is just wild with diffraction spikes. Some stuff is much nearby. This probably is a relatively nearby dwarf galaxy. It's intrinsically very blue, and if you look at the raw image, there's lots of structure, fine structure visible within it. And sometimes X marks the spot. What was quite surprising was that a lot of large galaxies that have an active galactic nucleus, like a Seyfert galaxy or other kinds of activity, while in the optical, you will not see anything particularly special about these galaxies. As soon as you go to really long near-infrared wavelengths, like 4 microns or so, that central source, the accretion disk around the supermassive black hole, shines through. It shines through whatever dust is around there that would block the optical light and the very near infrared light. And that means that if you see these diffraction spikes emanating from a central point source in a galaxy, you probably detected, okay, this is one that is an active nucleus. It has a supermassive black hole that's feeding. And in some cases, it can still be a really, really, really dense core, just a stellar core. In that case, the diffraction spikes tend to be somewhat fuzzy. And in other cases, the diffraction spikes are really crisp, in which case we know for sure that's a point source. Again, there's examples here of galaxies that show lots of this fuzz around, maybe even shell-like structures. That tells us something about how these galaxies came together. It's probably evidence that this galaxy grew out of eating up some smaller galaxies in the distant past. And then there's these extremely red blobs. This image is at a different scale than this one. This is a much smaller blob, but it's only visible in the 2 very longest wavelengths filters that we observe here. Tentatively, you would think that these objects are at a really high redshift of 11 or 12 or 13. But the striking thing of these images is also that there's too many of those, and they're too large and too bright. So apparently there's a different kind of galaxy here as well, like dusty galaxies that have lots of dust in them, maybe dust with a slightly different composition or particle size that can absorb light in such a way that it shows up as a relatively large and bright, but intensely red object. So these are objects that are at redshifts of 6 or 7. So that's still relatively far away, but not these pristine first generation of galaxies that everybody's hunting for. It's also clear from this image from how stark the contrast can be between intensely blue and intensely red galaxies in this image. More of this jumble of stars and star streams on the left, and another example of something going on in the center here, because we see that there is some diffraction spikes, faint diffraction spikes that are red, that are jumping out there. And then last, a pair of galaxies, a nice big spiral, even though it's still at a respectable redshift, probably more than 1, and a much nearer galaxy that shows lots of structure in it, lots of knots of star formation in there. Maybe even some evidence that there's some dynamical thing going on, maybe again a dwarf galaxy or so interacting or merging with a bigger galaxy. So that's my first view for you on what JWST can do in a field like this. Now, to get really to why we selected this field, we have to re-observe this field over and over and over again and find for things that change over time. So we had a proposal in for the next cycle. We have to wait whether or not that gets granted or not. And there's other teams as well that have nothing to do with me or our team that have their own idea of what they can do with this field. And that's great because we developed this as a community field. So it should be a field for everyone. This first data set is public, it was public right away from day 1. Anyone can download it from the archive. And since this was made into a press release, the pretty pictures are downloadable as well from either the NASA weblog or there's a zoomable version on the ESA website all around December 14th of last year. And then the last thing I want to show you is okay, we now have 2 of these areas covered. So what I've showed you the pretty pictures for is all associated with this southern spoke. But we now have also, as of December, this second spoke that is observed. In this rendition, I also show you where another instrument's footprint is, because we did not take observations with just NIRCam, but we turned on the NIRISS instrument as well. And that means that for a portion of this field, so the inner portion of this field, after 180 days, you get overlap with a portion that can be observed with NIRISS. So when we observed this first spoke, the NIRISS field of view was here and did not overlap with anything yet. Then we observed the second spoke, and the NIRISS observations fall here, also did not overlap with anything yet. Next Monday, we'll observe this top spoke, and that's the first spoke where we will overlap a little bit of where we have NIRISS data and where NIRISS data will overlap where we have images. And hopefully we'll be able to combine the imagery with the spectroscopy there and learn about maybe emission line objects that we didn't know were there, objects of types that we didn't know existed. And in other cases, merely, okay, how far away are these objects? That overlap is not for the whole area, it's just for a subset, but it's a subset, sub-area that's large enough that we will still have thousands and thousands of galaxies where we can do this for. And that concludes my presentation. So thanks again for inviting me. And
Thank you. Excellent. Questions?
I think so.
Okay. You said you were going to do spoke 1. You have to redo the shape of it.
As close as possible. We want to maximize the area of overlap. But there's multiple ways of going about it. And in many cases, going with a slightly more regular pattern or in a slightly different way, you can still get the signs out. But so it depends on when observations would be scheduled. And if we want to do this follow-up, do we really want all these filters or maybe only a subset of the filters? Like having all the filters allows us to characterize all these objects. But once you know what they are, you don't need to do it again. But you do want to have then, say, a long wavelength and a short wavelength filter to see if their brightness changed or if the position changed. So the follow-up is cheaper than this initial exploration to schedule. It's contained within a radius of 7 arc minutes or a diameter of 14 arc minutes. Now, because JWST is such a large telescope, its intrinsic plate scale is really, really fine, and its intrinsic field of view is quite narrow. So a typical camera is of the order of a few arc minutes across. So 14 arc minutes is actually a very wide field in terms of JWST imaging. A good question. So we exposed roughly 1 hour per filter. Oh. Yes. So the question is, what roughly in round numbers are the exposure times used for these observations that I showed? And it's roughly 1 hour per filter, but you get 2 filters at the same time, one short wavelength filter and one long wavelength filter. So that makes it more efficient in terms of observations, but the effective exposure time per filter still is 1 hour.
28 or something. There we go. Magnitude
Yeah.
28 is amazing. What's the bright limit for these instruments?
It varies a little bit what you can still deal with in terms of saturation. We try to avoid anything brighter than 15.5 magnitude, because that would saturate the detector so deeply that it becomes unrecoverable. Now, at a magnitude of 19, you will already start saturating. And because the telescope performs better than we dared hope, it actually starts saturating early than we bargained for. And that means that in many cases, you will have saturation effects. So the raw data will have holes in a lot of the point sources and the cores of galaxies. So you have to go back to the individual readouts, because these detectors are read out non-destructively. So instead of reading out once and then starting over, you read out and you sense how much more signal is in these pixels. And that means that as long as you're not too bright and too saturated, the first few reads may still be acceptable and valid. And then you toss everything afterward because it's saturated. But during those first reads, if you can still determine what is the slope, the rate at which photons were coming in, you're fine. You can still use the data. But yeah, it's unusual to think about a 19 magnitude saturating your detectors.
Where is it controlled from? Do you execute the viewing yourself, or you submit a plan and they do it for you and then you get the data afterwards?
Yeah, good question. Unlike a telescope that you have in your own backyard or where you can go to get a key and do everything yourself, you're not allowed to touch anything on JWST for very good reasons. So typically you have to submit a proposal, and along with that proposal, you have to have a technical implementation. So every observer, every proposer needs to download a piece of software, specify in excruciating minutiae exactly how these observations should take place, what filter to put in what filter wheel when, what kind of readout pattern, where to point, how to dither. All that stuff has to be defined ahead of time in that software. That software then gets sent to STSCI in Baltimore. They convert the information from that software into something they can use for their programming of the telescope. They construct typically a week at a time, a timeline for a week of observations. They upload that to the telescope ahead of time. And then if nothing goes wrong, JWST will perform all those instructions during a week. If something goes wrong, of course, then you need to interfere and the same day. It's really fast. I think there's typically at least 1 8-hour time slot that data is coming down. And in many days, there's double or triple that, in which case you pretty much have constant data coming in. That essentially all gets ingested in Amazon Web Services. That's where all the data processing is done. The JWST pipeline turns this raw data and the raw telemetry into a science product that can be used, that tells what it means that there is a certain signal in a certain pixel. It converts that into a uniform brightness that's calibrated. It tells me where that pixel really maps onto the sky, at least to first order. And then when you get the data at home, you download it and get it at home, same day or the next day. It's large data sets, so sometimes it's the next day. Then you typically have to figure out, okay, is this good enough for my purposes, or do I need to do additional processing? Because the pipeline is supposed to get you data that is maybe good to 5 to 10% accuracy in pretty much any parameter you want to choose. If you want to do better than that, you'll have to run more software on these data, calibrate it further, align it better, and yeah, do quite a lot of processing steps to make it look like I showed there. And then, of course, for public outreach images, they go yet one step further, where they clean up even more of the background. But at that point, you should not use the image for science anymore, because you have really changed, you have altered some of the characteristics of the background pixels. But it shows to the best extent what the data can deliver.
Question for Claude. Are you going to implement a submission process like this for Greco?
I think there were thousands of person hours involved in creating the software that they're using, many, many years of effort. If you can copy it and just implement it, maybe, but it's not an easy task.
There is a follow-on question. How much data comes in daily, the quantity, terabytes or?
It varies day by day, but the maximum data rate that you can generate in one day and still get to the ground without running out of storage space on the spacecraft or transmission bandwidth to get it down to Earth is of the order, I think, of 57 or 58 gigabytes per day. But that is highly compressed data in a reduced number of bits per pixel and so on. So once you actually feed that into the JWST pipeline, it pretty much explodes. It becomes so much larger. So the typical image size of one single shot, one image, is about 3.5 gigabytes once it has been reduced.
Okay, and there's one more, Rick Scott, if you want to ask your question.
Of course, it depends which instrument you're talking about. Some instruments have only a single detector. That's, of course, far less than for NIRCam, where you have 10 detectors that all push that data down to Earth for every exposure you take.
Okay. Can you hear me okay? Can you hear me okay? Last time the mic was really weak.
Just read the question because we can't hear.
So Rick was asking, you mentioned dithering. How's dithering done? How's dithering done with the JWST? Is the 1 hour exposure divided into shorter frames that are dithered?
Yes, that's an excellent question. Indeed, that's how we do it. For very, very small dithers, you can use a little pickoff mirror and move your field of view that way. But for most of the dithers that we employed here, we actually move the spacecraft slightly. So you use the reaction wheels on the spacecraft to move it, then make sure that you have full control over that motion by using the FGS, the fine guidance sensors, to make sure that you keep track of where your guide star is going and that that's indeed where it should go. And then you take the next image. It turns out that for various reasons, it's more efficient to just use JWST's reaction wheels and do the full dither pattern, get all these short exposures in one filter, then move to the next filter and do it all over again, than to sit on one dither position and then cycle through the filters and then go to the next dither position. Very often on the ground and with other telescopes, that's not the case. But the filter wheel on JWST and NIRCam is so large, and there was a real worry that the total number of moves that people would push that filter wheel through would exceed its warranty. So they said, for no, just move the telescope and limit how much you move that filter wheel. And it works. It's slightly less efficient in terms of time. Your overhead is slightly larger, but it works just fine. It's amazing how much control the software and the fine guidance sensors and these reaction wheels have over the telescope.
I may have missed it, but in the time domain, what's the expected resolution and relative magnitude over years as you're acquiring these subsequent exposures?
If we just have two separate epochs where we have observations, then it's limited by the sensitivity of that single epoch. And that gets us still of the order of high 28 magnitude. It's very faint. It's about 3 magnitudes fainter or more than you can do from the ground with LSST. Now, if you have already built up over time a very deep image from all these separate epochs, such that your reference image does no longer add to the noise, and your noise is entirely determined by the new epoch that's coming in, you can do slightly better. Depending on what source it is, how much it varies in brightness and various other details. But it's still, for most cases, in order for you to detect that it in fact did vary, you cannot go much deeper than the single epoch exposure.
What ground stations receive the JWST data? I mean, is it the Deep Space Network or is there another network?
I think it is going to the Deep Space Network. I think the main antenna is in Australia. But I think there's other antennas that can be put into service when and as needed. Of course, when there's an Artemis mission going up, then all bets are off because they hog every bit of bandwidth they can get. So yes, so we were worried for 2 of these spokes that it was awfully close to a planned launch. And that meant that a lot of these JWST timelines, they were interrupted or were revised to be as little data intensive as possible. And our program is at the limit of what you can do. It's very data intensive. We get every data and every exposure we can get in the time allotted. But luckily it all worked out.
Got 2 more online questions. Follow up by Jeffrey Sykes. Are there plans to use AI to analyze and process the data?
I'm sure some people have plans. I am not well versed in AI, but I know that there is people that work on deep learning and multi-layer AI neural networks. But what exactly they do and what exactly, or how they will interpret what they find, I don't know. That's not my specialty. But I can imagine that, especially especially once you have characterized already what is typical, AI can be very efficient in finding anomalies or things that don't match anything that's already known. And the sheer volume of data that comes down from JWST and the sheer number of objects that you are detecting, that precludes really going the manual route and going through it one by one. Now, of course, there's other people that hope to employ, say, Galaxy Zoo or Zooniverse, which is a crowdsourced platform. And they have been very successful for Hubble data and for SDSS data to find very anomalous objects that would not otherwise have been discovered. So my hope is high, but I have little specific information there.
Okay, great. And John Conrad has a question. How many hours per day is the telescope being used taking images? And how many hours per day spent pointing and maneuvering? And is it ever allowed to just rest?
Not if any astronomer can help it for the last question. But of course, yeah, there's overheads involved with anything. With Hubble, for most areas in the sky, your view is blocked by the Earth itself. So you typically lose half of your time anyway. So that should be used to put JWST in context. Like high hopes initially were that, okay, we're in L2, so we should be able to observe 100% of the time, right? Well, that's a little bit naive because there's lots of observatory housekeeping efforts that need to be done. Some of those can be done in parallel with observations, but not all. Certainly not things like momentum unloading. You don't want to be observing when you do that. In some cases, getting the data down to Earth will narrow what range of angles you can point at during that time. I think that for most of the time, they can just download data while observations are going on. But in general, if you observe or go to a new target, on average over all targets, over all sky, that costs about half an hour because it's a very big observatory. So it's slow to move. You cannot just zip from one part of the sky to another part of the sky. So every observer, every observation is charged this half hour right from the get-go. That's an overhead. Then every time you move a mechanism, that typically takes from several tens of seconds to maybe 2 minutes or so to complete. So that gets taken out of your observation. Every time there is an observation, you have to compile the specific instructions. So that takes a little bit of time. When you move your target, or sorry, within your target, like that dithering that we talked about, if you move the telescope, everything about the telescope once you're there tends to still wiggle a little bit. Now, luckily, it damps out fairly quickly, but that wiggle time is sort of like a rest time where the telescope does nothing else, just maybe some compilation, getting ready for the next exposure, but it lets that wiggle die down. So for these NIRCam and NIRIS observations that I showed, our overall efficiency was of the order of 57%. That means that, of course, then 43% effectively is overhead in one form or another, either from moving to the field, moving within the field, doing stuff with the instruments to get it ready for observations. It's very hard to do better than that if your overall exposure time is not much more than an hour. If you sit somewhere and keep observing for days at a time, you can do better because then you don't move, your overhead, especially your relative overhead, goes down. You don't go from field to field. But yeah, so count on somewhere between 43% on the good side to anything as much as 90% if you really want to have little snapshots and go from target to target.
Any other questions?
So I've got asked this one. You probably always get asked it. Let's see, so far, what's the deepest redshift confirmed galaxy? And when is there an observing plan schedule that you think is going to try and go deeper?
The deepest spectrum, the farthest away, most distant galaxy that I've seen an actual spectrum of, a NIRSpec spectrum, had a redshift of, I think, 13.7, if I remember correctly. And that was, there was absolutely no question about it. It had 2 emission lines that were clearly identified and hints of more. There's no question that object is at the redshift that's being claimed. Now, initially, last summer, when the first observations came in and people started hunting for extremely distant objects, there were claims of redshift of 20 and redshift of 15 and 16. That's all bogus. None of them are those redshifts. At that time, the calibration of the individual cameras, the calibration of the individuals within the individual filters and detectors within these cameras was not at the level yet where you could make such claims. Because if one filter, if you think it's at a certain brightness, but in reality it's at a different brightness, the fit that you're trying to do, it will find a solution. It's just the wrong solution. So a lot of those redshifts eventually came down when these better calibrations became available. A lot of them wound up in the redshift 6 to 9, 10 range, maybe a few 11. If you only have filters and no spectra, it becomes a little bit messier. You can get lucky in some cases that you really do detect an object and you get the right redshift. You just have difficulties proving that it's the right redshift because there will be a certain fraction of nuisance objects that wind into your sample. They ostensibly have the same redshift. It's just that in reality they don't. When you have like 7, 8 filters in the near infrared, and especially if you have a really, really deep Hubble image in the optical that can be used as sort of a veto image, then you do a little bit better. You can cut down on these numbers of interlopers. But frankly, I don't know whether I've seen a redshift I said, okay, this is beyond the shadow of a doubt that was beyond 13.7 or so. That made a nice press release, of course. They made the most of it. And that was not just one object. They also had some redshift 11 point something objects, 12 point something. So they clearly had a sample of very, very high redshift objects there.
No, doing great. Thank you, Dr. Jansen. We really appreciate your talk. It was really interesting. There are a couple of just logistic things. I forgot to mention that on Wednesday, Dave Perriott and I did a community event in Superior, and we drove by picket post. There is no ranger. The gate is open. That was effective Wednesday night. I have no clue about the future, but for now, picket post looks like it's available. There are some folks who are going to go out to the Union Bar and Grill, which is at Baseline and Higley, west side of the street, north end of the shopping center. So if some of you want to go out and just chat and maybe be able to join us, Dr. Jansen. As far as the room goes, we need to take up half of the chairs, so one rack of chairs. All of the green tables, leave the white tables up. We may take a few of them down, but we need to reset the room for something tomorrow. Otherwise, thank you for coming. We really do appreciate you, and we will see you next month. When I said April, whatever,